In last two lectures we had seen identity theorem, the statement of identity theorem, and some examples based on that. Right. So again let us recall what is the identity theorem. So if D is a domain, that is if D is an open connected subset of C, and if we have an analytic function on D such that zeros of f as a limit point in D, then the function is zero function, means f of z equal to 0 for all z in D, the domain. We have also seen its corollary. So it says that if we are given a domain D, if we are given two analytic functions on D such that the set of points where these two functions are equal has a limit point in D, then the functions f and g are turns out to be the same one, means f of z is same as g of z for all z in D. So we had seen some examples based on this one, so let us see some more examples today. So I think we had seen this last example, so let us go for the next example. So let f be analytic on a domain D, and it is given that f of f is 0 at a point z0 of the domain D. Then what do we want to show? Then we have to show that either f is a zero function or there is a deleted neighborhood of z0 such that f is never 0 on that deleted neighborhood. So this statement can also be written in this way. It means what? The zeros of a non-zero analytic function are isolated. See, that is what the statement says. If f is not identically zero function, then, and if we are given f of z not equal to 0, then there is a deleted neighborhood of z0 such that f is never 0 on this deleted neighborhood. So again we have to show either the first statement holds or the second statement holds. What do? We assume that the first statement does not hold, and then we want to show that the second statement is true. So let us see how we do that. So as I said, we assume that f is not identically 0. Because f is not identically 0, f is a function on D, it is not identically 0, and so okay, this is what we are assuming. Now we want to show there is a deleted neighborhood, so we again assume that the second statement does not hold, and then we try to get some contradiction. Okay, suppose that every deleted neighborhood of z0, suppose that in every deleted neighborhood of z0 there is some point at which the function is 0. Again I am saying, what do we want? We want to prove an existence of a deleted neighborhood of z0 such that f is never 0 on that deleted neighborhood. So we are assuming that that statement does not hold. Means what? Whatever deleted neighborhood of z0 we take, there exists some point in that deleted neighborhood at which the function is 0. So if we consider the open ball with center z0 and radius 1 minus z0, means it's a deleted neighborhood. So by our hypothesis there exists some point z1 in this deleted neighborhood, so that f of z1 equal to 0. Okay, now what we do, we take r2 to be minimum of 1 by 2 and mode of z1. See, note that z1 is not equal to z0, right? So now we take r2 to be minimum of 1 by 2 and mode of z1. So again by hypothesis, I mean what we've assumed, it says that there exists some point z2 in this deleted neighborhood such that f of z2 equal to 0. We do the same process now. Now we take r3 to be minimum of 1 by 3 and mode of z2. Okay, why we are doing this? In fact, one can see that z1 is not equal to z0. Now z2 which we found, that is not equal to z1. Why? Because r2 is less than or equal to mode of z1, and therefore Z2 is not equal to Z1. Now we take R3 to be minimum of 1 by 3 and mode of Z2. So again by hypothesis we get some Z3 in B Z0 R3 minus Z0, which satisfies f of Z3 equals 0. So we keep on doing this, means we are going to use induction. So by using induction, what do we get? We get a sequence Zn in a domain D, such that what? F of Zn equal to 0 for all n. This is sequence we get. Let us see also, as I said, the points Zn are distinct. And the third condition is that, see, Zn is where, one can see that mode of Z3 minus Z0 is less than R3, and R3 is less than or equal to 1 by 3. So, since we are using induction, what do we get? Mode of Zn minus Z0 is less than Rn. Rn is less than or equal to 1 by n. This is what we are going to get for all n. Right. And so, because f of Zn is 0 for all n, the set Zn is contained in the set of zeros of f. Right. As I said, Zf is the set of zeros of f, and as all the points Zn are distinct and Zn is converging to Z0. Why Zn is converging to Z0? Because mode of Zn minus Z0 is less than or equal to 1 by n. So we got a sequence of distinct points which is converging to Z0, and therefore Z0 is the limit point of the set Zn. And because Zn is contained in the set of zeros of f, Z0 is a limit point of Zf. And what is the hypothesis? We know that f is analytic on a domain D, and the set of zeros of f has a limit point Z0 which is in D, and therefore by identity theorem f is identically 0. But we assume that f is not 0, and therefore our assumption that in every deleted neighborhood there is a 0 of f is false, and that means there exists a deleted neighborhood of Z0 on which f is never 0. And again I am repeating, it means what? Zeros of a non-zero analytic function on a domain are isolated. Means given a 0 of a non-zero analytic function, there exists a deleted neighborhood of Z0 which contains no 0 of f. Okay, and this is not possible as I said, so our supposition is false, and therefore the second statement is true. Okay, so now we have seen in identity theorem that D is a domain, means it's an open connected set, and if we are given an analytic function such that the set of zeros of f has a limit point in D, then function is identically 0. So now we give two examples. We cannot drop the condition that D is a domain, means D is connected, and the second condition that the set of zeros of f has a limit point in D, that condition also cannot be dropped. So first example we give where the open set is not connected, then we show that the identity theorem does not hold. So what we do, let us take D to be ball with center 0 radius 1 union ball with center 3 and radius 1. So D is a disjoint union of two open balls, so D is an open set. One can see that D is not connected. Right, now we define a function f from D to C by f of z equal to 0 on the first ball, and we define f of z to be 1 on the second ball. Then f is analytic on D. Okay, one can see that f is 0 only on the set B01, and that means ZF, the set of zeros of f, is what? B01. Now the set B01 has a limit point, namely 0, which is in the open set D, but the function is not identically 0. So in identity theorem we require that the open set D should be connected. If it is not connected, then the conclusion may not hold. Now what is the second condition there? If D is a domain, F is analytic on D, and another condition we require is that the zeros of F should have limit point in D. So now we show that if the limit point is not in D, then again the statement of identity theorem or the conclusion of the identity theorem does not hold. So for that now we are giving example. So now we take D to be what? Ball with center 1 and radius 1. Now we define a function f from D to C by f of z equal to sine pi z for all z in D. See, pi by z is analytic function because this ball does not contain 0, so there is no problem. I mean, one may talk of pi by z. So pi by z is analytic, sine is an entire function, so the composition is analytic, and therefore this function f is analytic on D. Right. Now we are interested in finding out zeros of f. As I said, this f is a non-zero function. Okay, now let us take any z in D. Then one can see that f of z equal to 0 if and only if z is of the form 1 by n for some n in n. See, here we don't have n in z because z is in D. So no real number, no negative real number is going to appear in this D. So f of z is 0 if and only if z is of the form 1 by n for some n in n. See, that can be proved easily because sine pi by z is 0 if and only if pi by z is of the form n pi, and that means z has to be of the form 1 by n. And that means what we have shown? That means we have shown that the set of zeros of f is 1 by n, n belongs to n, and this set has a limit point, namely 0, which is not in D, and this function is not identically 0. So what we have shown? We have shown that the zeros of f has a limit point, but that is not in D, so we cannot apply the identity theorem, right? And as I said, f is a non-zero function. So both the conditions, the open set D should be connected, that is necessary, and the set of zeros of f has a limit point in D, that is also necessary. Let us go for next example. Again, I mean, all examples they are based on the identity theorem. So let f from D to C. Again, I'm saying this script, I mean this D stands for the open unit disk, means it is the collection of all those z in C such that mod of z is less than 1. So let f from D to C be a non-constant analytic function. Which of the following conditions can possibly be satisfied by f? The first condition is f of 1 by n equals f of minus 1 by n equals 1 upon n squared for all n in n minus 1. We cannot include 1 because this D does not contain 1. So this is the first condition. Means the question is, does there exist a non-constant analytic function f satisfying this condition? Another question, does there exist a non-constant analytic function f satisfying the condition f of 1 by n equals f of minus 1 by n equals f of 1 upon 2n plus 1 for all n? The third condition, does there exist a non-constant analytic function on the open unit disk D satisfying mod of f of 1 by n is less than or equal to 2 power minus n for all n in n minus 1? And the fourth condition, again I am saying, does there exist a non-constant analytic function f on D satisfying 1 upon square root n less than or equal to f of 1 by square root n less than or equal to 2 by square root n for all n? So we shall see answers, and if we show that if such a function does not exist, exist, we shall give arguments for that. But the first one is much easier. You can guess a function which satisfies this condition. In fact, that function is f of z equals z squared. So there exists a non-constant analytic function f satisfying the first condition, and in fact that is the only function that can again be proved by using identity theorem. So answer of the first one, I said take f of z equals z squared, then the condition 1 is satisfied, so there exists a non-constant analytic function on D which satisfies the first condition. Now we shall show that there is no non-constant analytic function which satisfies condition 2. Okay, so let us see how we can do. So let f be an analytic function on D which satisfies condition 2. That means what? F of 1 by n. We are not considering the part f of minus 1 by n. Let us first concentrate on this f of 1 by n. So the condition we are having that f of 1 by n equals 1 upon 2n plus 1, and that is same as 1 upon n divided by 2 upon 1 plus n. And as we had seen in an earlier example, that we can prove that f has the form z upon 2 plus z. So we take g of z to be z upon 2 plus z. Then g is an analytic function. Why? Because minus 2 is a singularity of this function g, which is not in D. So g is analytic, and g of 1 by n is same as f of 1 by n. And so the set of points where g and f are equal contains the set 1 upon n belongs to n minus 1. And the first set has a limit point, namely 0. That means 0 is a limit point of the set z in D such that gz equals fz. So by corollary of the identity theorem, what do we get? F of z is same as g of z. But what is g of z? Z upon 2 plus z, and so f of z is z upon 2 plus z. But then one can see that the condition f of minus 1 by n equals 1 upon 2n plus 1 does not hold, and thus there is no non-constant analytic function satisfying the condition 2. Because see, if this condition is satisfied, that means f of 1 by n is same as 1 upon 2n plus 1, but then it is going to give us f of z is z upon 2 plus z. But then the another condition, namely f of minus 1 by n is 1 upon 2n plus 1, will not be satisfied. So there is no non-constant analytic function on D which satisfies the condition 2. Now let us see the next example. Now what is given? We again assume that there exists a non-constant analytic function f which satisfies the condition 3, means mode of f of 1 by n is less than or equal to 2 power minus n. Let us see then what happens. Okay, because f is analytic, f is continuous, right? F of 1 by n is tending to 0, and 1 upon n is tending to 0 because of continuity of f. F of 1 by n tends to f0, but f of 1 by n is tending to f0, and therefore what do we get? F of 0 equal to 0. Again I am saying f is continuous at 0, and what we have? 1 upon n tends to 0. Therefore f of 1 by n tends to f0, that we have, and by this condition f of 1 by n is tending to 0, and therefore f of 0 equal to 0, right? We have already shown that zeros of a non-constant non-zero analytic function on a domain are isolated. So we are given that f is a non-constant function, f of 0 equal to 0. So 0 is an isolated zero of f, and it is known to us that zeros of a non-zero analytic function have finite multiplicity, and therefore we get some k and an analytic function g on D such that f of z is of the form z power k into g of z, and one more condition that g of 0 not equal to 0, right? So because g is analytic and g of 0 not equal to 0, by continuity of g at the point 0 we get some epsilon positive such that mod of gz is greater than or equal to mod of g0 by 2 for all z satisfying mod of z less than epsilon. Again, only continuity of g at 0 is required. Okay, so now we take any natural number n which satisfies the condition 1 upon n less than epsilon. So for this 1 by n, what do we get? Mod of g1 by n is greater than or equal to mod of g0 by 2, because 1 upon n is less than epsilon. Okay, and this is the condition we have assumed, and so for this n means natural number n satisfying the condition 1 upon n less than epsilon, what do we get? See, mod of g0 by 2 into n power k is less than or equal to, see, as I said, mod of g0 by 2 is less than mod of g1 by n by this condition, and n power k is written in this way, right? Now one can see that what is f of z, z power k, or z power k into gz is what? Fz. So by using that, what do we get? Mod of g0 by 2 n power k less than or equal to 1 upon n power k mod of g1 by n equals f of 1 by n. See, what will be f of 1 by n? F of 1 by n will be n power k into g1 by n. That is what is written here. So this is what we have. So now let us forget this term, I mean these two terms, namely 1 upon n power k into mod of g1 by n. What do we get? Mod of g0 by 2 into n power k is less than or equal to 2 power minus n. Now this is true for which n? This is true for every n satisfying the condition 1 upon n less than epsilon, means this inequality is true for every large n. But now if we take n by k in the denominator, what we are going to get? We are going to get mod of g0 by 2 is less than 1 upon n power k into 2 power n. But this 2 power minus n into n power k, 2 power minus n upon n power k tends to 0 as n tends to infinity, and that means what? Mod of g0 will be 0, and that gives us contradiction, and therefore our assumption that such a function exists is false. Okay, so now let us go for the fourth possibility. I mean, what do we need to check? Does there exist a non-constant analytic function on D which satisfies the last condition, namely 1 upon square root n less than or equal to mod of f of 1 by n less than or equal to 2 upon square root n? We show that such a function does not exist. Let us see how we can do that. So let f be a non-constant analytic function which satisfies this condition. We are going to get contradiction. So again, if we use the first inequality, and the way we have argued in the last example, it says that f of 0 must be 0. Again, because f is analytic, f is continuous, 1 upon n is tending to 0, so f of 1 upon n will tend to f0, and by this one the limit of f of 1 by n is 0, so we get f of 0 equal to 0. And because f is analytic, it is differentiable at every point, so this limit has to be same as f dash 0. See, there are two equivalent conditions for the limit. Limit z tends to a, f of z equal to L if and only if for any sequence of xn, none of xn equal to a. If xn is converging to a, then f of xn will converge to the limit. So because we are interested in limit at 0, so we are considering 1 upon n. So 1 upon n is tending to 0, and because f is differentiable at 0, this limit must exist and it has to be same as f dash 0. Okay, this limit is f dash 0. Okay, now we take any n. This is what I made a mistake. I should write n minus 1. Then f of 1 by n divided by 1 by n. What is known to us? F of 1 by n, mod of f of 1 by n is greater than or equal to 1 upon square root n, and 1 upon n as it is, so that is going to give us square root n. But then the limit of f of 1 by n upon 1 by n is not going to exist, because square root n can be made as large as we want by taking n large. So this is a contradiction. Because f is analytic at 0, so f is differentiable at 0, this limit should exist and must be f dash 0, but here we have shown that this limit does not exist, and therefore there is no non-constant analytic function on the open unit disk D which satisfies the condition 1 upon square root n less than or equal to mod of f of 1 by n less than or equal to 2 by square root n. So that example is over. Okay, so now we see another interesting example. Let f be an entire function such that what, given a complex number a, there exists some n in n0. n0 means n union 0 such that fn at a is 0. Fn means nth derivative of f at a. Fn means the nth derivative of f, and when n is 0 means the function itself. A 0th derivative of a function is the function itself. So we are given that given a in C, there exists some n in n naught such that fn of a is 0, and then we want to show that f is a polynomial, right? See, in fact, you can see the converse part easily. If f is a polynomial, say of degree n, then n plus 1th derivative will be 0, so n plus 1 is going to work for every a in C. So in fact this is a characterization of a polynomial. So one part is easy, as I said. So now we want to show this part. Okay, so to show f a polynomial, what do we need to do? If we can show that for some n fn is 0, then f will be a polynomial. How? That you need to check, right? To show f polynomial, we need to show that some derivative of f is a 0 function. Okay, we first note that any uncountable subset of C has a limit point, and this you can do as an exercise. You need to show that any uncountable subset of C has a limit point. Another exercise you can do is that all the derivatives of f are entire functions. How? In fact, you can use Cauchy integral formula. If you see Cauchy integral formula, it says that any derivative of analytic function is an analytic function. Okay, so these are the two facts we are noting. The first one is any uncountable subset of C has a limit point, and the another one is if f is analytic on an open set, then all the derivatives of f are also analytic, and that follows from Cauchy integral formula. So these are the two results we are going to use. So for n in n naught, we define or we take zfn to be all those z in C such that fn z equal to 0, means it is the set of zeros of nth derivative of f. This is the set of zeros of nth derivative of f. Now take any a in C, then by hypothesis what is going to happen? There exists some n such that fn of a is 0, because that is the hypothesis. If a is in C, then there is some n in n naught such that fn of a equal to 0. What does that mean? This a is an element of z fn, and that means C is nothing but a union of all these zfn. How? Again, see, one way is obvious. The union of all these sets is subset of C. Now what we have done here, we have taken any a in C, and then we have shown that a is in at least one of these sets, and therefore C equals union of all these sets. Okay, now we claim that at least one of these sets zfn is uncountable. See, if all these sets are countable, then countable union of countable sets is countable, that is known to us. So by using that, what do we get? The union will be countable, but that means C is countable. That is not true. Again, if each of zfn is countable, then their countable union will be a countable set, but that means C will be countable, but we know that C is uncountable. So there exists at least one n such that zfn is uncountable. So as I said, because the set C is uncountable, we get at least one n in n naught such that zfn is uncountable. Now because this zfn is uncountable, it's an uncountable subset of C. By the result we have noted, any uncountable subset of C has a limit point, so the set zfn has a limit point in C, right? But we know that fn is an analytic function on a domain, the whole complex plane, and therefore by identity theorem fn, again I forgot to make brackets here. So by identity theorem, what do we get? The nth derivative of f is identically 0 function. And what does that mean? F is a polynomial of degree at most n minus 1, right? So we stop here. We'll see some more examples in next video. Thank you.